So, I have discussed about the defect in last class, because defect is the main origin of ionic conductivity. So, for the experiment, what is the working formula we will use? So, that we should understand this working formula. So, working formula basically, so there are few mechanism of ionic conductivity, because ion has to move in a electric field, then only we will see ionic conductivity. Okay. So, there are few mechanisms for this ionic conductivity. So, one is basically diffusion of impurity atoms or ions at interstitial positions from the lattice point, that ions or atoms can diffuse to the interstitial position, then basically it is creating a vacancy going to the interstitial position. Okay. So, also as I told this, it could be due to the diffusion of vacancy. So, to diffuse the atoms inside the solids, so it needs energy basically. So, in order to diffuse an atom, the potential energy barrier from where it is coming, presented by its neighbors, because neighbors, these are also atoms. Okay. So, when original atom from a site, lattice site, when it will try to move, then other atoms, neighbor atoms will not prefer that one. So, there will be electrostatic repulsion, right. So, that is basically is barrier. It is the barrier, always we express in terms of potential barrier. It is like height. So, to diffuse means to cross that height, to cross that barrier, it needs energy. If this energy is, this height is say E, then the probability of jumping the barrier is exponential minus E d by k t, E d for diffusion. Okay. So, to diffuse an atom in a crystal, so it has to cross the barrier. If that barrier height is E d, then probability to toss, probability to diffuse is classically this exponential minus E d by k t. So, from where it will get that energy? It will get the energy basically from the thermal energy. So, the energy will be supplied from the temperature, increasing the temperature. So, energy will be k t. So, now competition between k t and E d. Okay. So, this is the classical probability. So, this is the probability of diffusion. So, now if there is a vacancy, then it will be easier to diffuse, because already place is there to go. So, if there is a vacancy, then the atoms will diffuse easily and it will go to the it will fill up that vacancy. So, that means what is happening? Ion or atom is moving forward, filling up the vacancy. Now, the original position of the atoms or ions, now that is vacant. So, as if this ion is moving forward and vacancy is going backward. So, if vacancy is there, so barrier height will be lower. So, to create vacancy, it needs energy. Okay. So, the probability of creating vacancy if phi energy is required to create ion vacancy, then the probability of a site to be vacant is exponential minus phi by kT. So, this phi is the energy required to vacant a site of lattice. So, vacancy helps in conduction, and also this ions has to move forward. Okay. So, when ions will move forward, so it has to cross the barrier. So, the two types of energy are involved: to diffuse, to move the ions. One is the we are telling the diffusion energy. Okay, energy required to diffuse, that's it's equal to the potential barrier presented by the neighbors atoms. So, that is E d, and another energy to create vacancy, that is phi. Okay. So, considering diffusion and vacancy creation, one can derive the conductivity exponent. There are some few steps, so I have not derived in details. So, one can write this conductivity expression, that sigma equal to some constant c by t exponential minus E d plus phi divided by k t. Okay. So, if you derive, then you can find the form of C, but I do not need this form of C. Experimentally, I can because my aim is to calculate the activation energy. So, without knowing this C, I can get that, as well as this. Of course, conductivity experimentally we will measure. I think this or C, you may need C value. I will get C value also I will get from the graph. And yes, without knowing details about the C, one can find out sigma as well as the activation is. Now, activation, so C by T exponential minus E A by K T. E A is the activation energy, whatever we want to determine. So, this in activation energy, basically two types of energy are involved, E d and phi. So, this E d is basically is the for diffusion energy required for diffusion, and phi is to create the vacancy, because both we need for conduction of the ions, because if vacancy is not created, ion will not be able to move forward. So, vacancy has to be created, it is going to the interstitial position. Now, next it has to get the vacancy. Okay. So, then only it will go there and as if the vacancy is moving in opposite direction. And of course, they are in opposite charge, you know. So, that is why it is like hole and electron. Okay, in semiconductor, they are moving in opposite direction, but both are contributing the current. Similarly, here if ion is positive, so positive vacancy means positive ion is missing. So, it will be equivalent to a negative charge. Okay. So, negative charge as if moving backward and positive charge ions it is moving forward. So, both will contribute in the conductivity. Okay. So, here you can see from this formula you can see, so sigma T, if you take log sigma T log exponential, this log sigma T equal to, it will be minus E A by k T and some constant log C, some constant will be there. So, log sigma T means if it is say y, then that will be equal to E A by k T plus minus something whatever, E A by k T plus log C, plus or minus log C whatever. Okay. So, y equal to mx plus c. So, this is a straight line and it will intersect the y axis, So, from this intersection basically you can find out c and E by k T. So, if you plot log sigma T versus 1 by T, then you will get the straight line, and from that straight line you can find out the slope, and from that slope will be equal to E A by k, value is known. So, E A one can find out, and also this from intersection you will find out this C value. Okay. So, you can find out the conductivity. You can find out the conductivity as a function of temperature, So, one can plot this graph after taking data, and from that data basically we will calculate the activation energy. So, the sample we will use, you see this sodium chloride is a ionic, it is a solid and ionic crystal. Okay. So, you may get the ionic conductivity. So, generally sodium chloride if you use in solution, then this is the ionic conductivity in solution, is not in solid. In solid condition also it will show ionic conductivity. Okay. In that case, which one will diffuse? See, it depends on the mass of the atom. So, lighter mass of the atom will diffuse fast. So, in case of sodium chloride, sodium will diffuse faster than chlorine. So, actually this ionic conductivity in sodium chloride will get because of the diffusion of the sodium. Okay. So, in our laboratory we will take the sample, this is basically bismuth vanadium bismuth vanadate. So, this is the formula. Actually, this metal is derived from bismuth, this Bi4 V2O11. Okay. So, half of it basically this is also stable material, bismuth vanadate. Now, if you doped copper 10% copper, if you doped replacing the vanadium. So, our sample ultimately this is the sample Bi2 10% copper and 90% vanadium, because copper replace the vanadium, 10% copper is introduced in this parent material, and then O 5.5. So, these sample are prepared by our student using solid state reaction method. After preparation, they have characterized the sample, structural characterization, and they found that this oxygen here it is not 5.5, but it is oxygen O 5.35. So, less oxygens are there. So, that means in this sample there is a oxygen vacancy. If oxygen vacancy is there, then this will show higher ionic conductivity at comparatively lower temperature. Okay. So, this will show easily this ionic conductivity even at the in the range of 500 Kelvin. Okay. Above the room temperature around 2 to 300 degrees centigrade, if you go up, then easily you will see this nice conductivity of this sample. So, that is because of oxygen vacancy and because of oxygen diffusion, because among these oxygen is the lighter atom. So, it will diffuse faster. So, both this oxygen vacancy as well as the presence of this lighter atom like oxygen. So, that is why this its activation energy will be lower. So, you do not need very high temperature to activate it. Okay. So, that is why this sample is chosen in our laboratory, so that within 2, 3, 400 degrees centigrade we can see the quite reasonable change of the conductivity, ionic conductivity of the sample. Okay. So, this measurement is very simple. Basically, you have to measure current and voltage, like we are going to measure the resistance, resistivity as a function of temperature. So, the experimental setup. So, this the manual is there, experimental setup I will show you, but the circuit diagram is very simple. So, you have a furnace, so sample is there, you have a furnace and sample is there. Okay. So, we will heat this sample using a temperature controller. Okay. Now, across this sample this voltage will applied, for a constant voltage there will be nanoammeter, because current will be very small. So, it will be nanoampere order. So, there will be nanoampere ammeter in the circuit. So, with temperature only we have to note down the change of this current for a constant voltage. Okay. So, circuit diagram is really very easy. I will show you the experiment. So, let us go to the experimental setup and see how one can perform the experiment. So, this is the experimental setup for ionic conductivity measurement and for determination of the activation energy. So, as I told that this measurement is very simple, it is It's a Ohm's law experiment basically. Circuit diagram is just here, you can see this is your sample. Okay. So, you should have provision to heat the sample and measure the temperature. So, for that you need arrangement, as well as you just this is the simple circuit diagram. So, you have applied a constant voltage and what is the current flowing through this circuit. So, that we will know from this nano ammeter or picoammeter. In this case here we are using picoammeter. So, naturally you can see this very small change of the current we have to determine. So, let us see our sample here. I can show you our sample. I think it is a slightly hot. So, this you see this tablet kind of sample here. Okay. This is a tablet kind of sample, this is the sample. So, thickness of this tablet is a pellet basically. Thickness of the pellet and radius or diameter of the plate is known. Okay. It is supplied, or one can measure also. So, now you see on top of this tablet, this one electrode and this bottom, from bottom this connection is taken from this electrode. So, one is on top and another is from bottom. This connection from top and bottom, these two electrodes, from these two electrodes, these are coming. So, these two are basically this, and so this is connected. There are one battery is connected. This battery is connected. It is a 1.5 volt battery, constant voltage it will give, and this other circuit is completed through this whatever nano ammeter I have written, but it is the picoammeter. Okay. So, here different scales are there, whatever reading you will see, we have to multiply with this one. So, this pico ampere into this reading. So, different range one can choose. Okay. So, now, so this is for, as I showed you, this circuit is made here, it is a simple circuit. Now, we need arrangement, basically heating arrangement. Okay. So, this green wire whatever you are seeing, that is basically thermocouple. It is connected close to the sample. So, it will give the temperature at the sample place. So, this is connected here. So, here temperature controller are there. So, we will get the reading of the temperature from here, whatever red font you are seeing, number you are seeing, that is basically present temperature. Okay. And 400 you can see here 400, that is the set temperature. Okay. So, oven is off, it is up, it is off. When I will put down, so this it will start heating. So, this is the oven. So, it is basically this is the power supply of the oven and temperature controller. So, through this it is the power to the heater is given. So, heater here, inside heater is there. So, power from here is given to the heater. Now, this furnace kind of things, okay, hole is there. So, I will insert this one through this hole. Okay. So, now my sample is in oven. So, and for protection, for less heat radiation, to reduce the heat radiation. So, this cover, we are using this cover. So, I will put this cover. Okay. So, now it is ready-made setup. So, inside things are there, I showed you. So, now this from this oven, present temperature it is 78, but I have set here these options are there 400, I can change this temperature. So, say if I wish to change this temperature say 450, so I can make it 450 here up 10, 20, 30, 40, 50. Okay. So, 450, then I set it. So, now it is set at 450. So, and this temperature is coming from the sensor, temperature sensor, and we are getting reading here. So, this part is basically for oven, and this battery constant voltage 1.5 volt. Now, we will change the temperature, we will put on the oven and change the temperature. At different temperature, we will note down this reading, and you should note down this whatever you have chosen here 10 to the power 10 square, okay, 100. So, whatever reading that is into 100 pico ampere. Okay. So, at present it is, then it is 6.5 nano ampere. Okay. So, we have to note down at this temperature, this is the current. Now, I will switch on the oven. Now, oven is switched on. Okay. Now, you can see the temperature will increase and it will go up to 450, and we should take reading say I think every 10 degrees centigrade step we can note down the reading. So, it is now 83, and that is the same value is so its conductivity is not changing with temperature at initial temperature. Now, 85, yes, 86, 87. So, it will change fast because I have set it is at very high temperature 450 degree centigrade. It is not Kelvin, it is a centigrade. Okay. So, 91, 90. So, at 90 one should take reading. So, it is now started to increase, but it is not increasing much. It is going towards 7 nanoamperes. 7 nanoampere. Now, it is 100 degrees centigrade. So, this is 7 nanoamperes. So, we will note down this reading. We will note down this reading. So, it is the when temperature will be around 200. So, that reading will be, I think the change will be very high. So, now 110 you should take, then 120, whatever the reading, say 7.5 nanoampere, at 120 7.8, now it is going towards 8 nanoampere, so it is the 138 nanoampere. Okay. So, this way, so let us see how fast it is changing. So, actually what we have to do, just we have to increase the temperature, we have to set 100 degree first, then go there, okay, then you change set to the 200 degree. So, then slowly it will increase the temperature and you will be able to take data smoothly. Okay. So, but since here just within short time I want to just demonstrate, show the reading. So, that is why I have put at highest value. So you can see clearly that the change is very fast now. Now it is 12 nanoampere. It's so from 6.5 now it is 12.5. Okay, it's almost 200 degrees centigrade. So it is 13 nanoampere. So since temperature change is quite fast, that's why this reading change also fast. So, but we should not collect data hurriedly. So, step by step we should set the temperature 100, 200, 300, then 400. Then this will temperature will change slowly and you can record the data peacefully. Okay. So, I think so this way you take up to 450. So, I think I will stop oven, still it may increase some temperature. So, this is a very simple experiment setup and measurement, everything is very simple, but from this experiment we can learn about the crystal defects. So, that's why elaborately I discuss about the crystal defects. So, what we learn from this, what physics we learn from this experiment, that is basically about the crystal defect, and without crystal defect it is not possible to get ionic conductivity. In ideal crystal it is impossible, almost slight conductivity you can get, but you have to increase temperature to maybe 2000 degrees centigrade. Okay. So, but that is not the realistic case. So, here that data we have to take, right. So, now from this data what you are getting? You have volt V equal to 1.5 volt, okay. And then current I you have in nano amperes, okay, some nano ampere. So, V, you have to find out E, electric field. So, that is V by T. What is the T? T is the thickness of the sample. Okay. So, that value is given, it is around 1 millimeter. So, V 1.5, so you know E, electric field. So, electric field is constant, but current is varying with temperature. So, you can find out the current from current density, okay, J. You can find out the J equal to I, what is the relation? I by A. A is tablet diameter, if its diameter is D, then T by 2 are the radius, so pi r square, okay. So, that is the area. So, you are noting down current I nanoampere, okay. You convert to the current density. Now, you know J equal to sigma E, J equal to sigma E, okay. So, from your data you can calculate sigma equal to J by E, okay. So, now we calculate sigma and you noted down temperature. So, sigma at different temperature. Now, plot graph. So, here our student plotted, they took data and plotted. I will show you, they plotted this, you see this current versus temperature. So, here you can see this initially the change is very slow, with temperature, then it become fast. Okay. So, this type of change one can see when activation energy is required. So, initially the temperature is not sufficient to activate the diffusion or creating vacancy. Okay. So, it needs minimum energy to activate it. Okay. So, that is why when temperature is just crossing the threshold, activation energy is above activation energy. So, then it is increasing very sharply. Okay. So, now as I told that you have to plot log sigma t as a function of 1 by t. Okay. So, some factor 1000 factor, but that does not matter. So, it is so 1 by t if you plot, then you will get straight line. So, it is a more or less straight line, very high. Yes, it is a very low temperature. So, low temperature is basically there will be some error because value is very small, close to the 0 value. So, that is why. So, now feed this data, If you feed this data from this slope, you will get, and from that slope is E by k, Ea by k, as I told, Ea by k. Okay. So, negative slope, it was minus there, so negative slope. So, k is known, you can find out E. Okay. So, that is why the determination of the activation energy from ionic conductivity. Okay. Yes, I think this is a very simple but nice experiment. It is a reach of physics in this experiment. At least this defect, what is defect that student can learn, and I also tried to explain in details. So, I will stop here. Thank you.